So I shall start. So today we have our second webinar of this year of the project IGCP 707. Today we have the pleasure of having Dr. Bernard Doll presenting his research on geochemistry and mineralogy of mining waste and its impact on arsenic remediation. Bernard Doll is the president and director of SUMIRCO, Sustainable Mining Research and Consultancy. He has been active in academia for the last 20 years in teaching and research in countries like Sweden, Chile, Spain, Peru, and Switzerland. He obtained his PhD at the University of Geneva, Switzerland in 1999 and received his habilitation, privat docent, in acid mine drainage formation, control and prevention at the University of Lausanne in Switzerland 2005. The main focus of his research and consulting activities is the mineralogy and geochemistry with applications related to the characterization, control, prevention, and remediation of environmental pollution. He specialized in the study of acid rock drainage in mine waste and ore deposits for a more sustainable mining operation. Thanks a lot, Bernard, for this presentation. And now it's your turn.
Thanks a lot, Jessica. Welcome, everybody. Do you see the screen?
Yes.
Okay. Okay. What I want to do today is give you a short overview about the PhD thesis. My colleague from Senegal, Nuyo Diaby, I hope he could also connect it. He wanted to connect. So he did a very nice study in southern Peru. And as your project is mainly focused on arsenic, I will focus also more in arsenic. If you want to know more about this project, you see here there are 3 papers, yet sometimes out, so you can refer to all the details when you need it. So the question is here, it's a pretty specific case how mine waste remediation intercepts the natural arsenic flow in a marine short tailings deposit. So there are many weird names. What is a marine short tailings deposit? And how can remediation of such a thing intercept the natural arsenic flow in the system? So let's, as we all cannot travel, so I will take you anyhow for a nice travel down to southern Peru. Here you have Peru, this is Chile, Argentina, and Bolivia, all friends here around, everybody very focused on arsenic because we have a lot of arsenic around there. But here in this area, we are looking on mine tailings which were produced many decades from 2 mines, 2 porphyry copper systems, Cuajone and Toquepala, operated by Southern Peru Copper Corporation. And at the time when they've been produced, they've been sent via the river into the sea, where in a bay they formed a marine short tailings deposit. Here you have a little bit more a close-up. You have in the high Andes the 2 mines, and then you have a river system where it enters in the Rio Locumba, and this goes in this Bahia de Ite, the Bay of Ite. And it formed here something like a delta. So we are having here tailings from 2 mines. They've been sent 120 kilometers from their origin into the sea. It was operating from 1960 to 1977. So there are about 800 million metric tons of tailings in this bay. It has a surface of 12 square kilometers and about 4% of sulfides. So here you have a zoom. Here you see the 2 mines. And This mine was then bought by Mexico Group, and they, at the time when they bought it, they could not send any more tailings into the sea, so they had to construct here new tailings impoundment. Quebrada Honda it's called. So the idea was to study what's happening with the tailings in the sea, but I show you some picture of the new tailings impoundment. So you see it's a really a major operation. It's nowadays it's much higher. It's most likely near this crest and it will go over it. So they have to put here additional dams. So this will be a enormous tailings impoundment. You see here the dike, and they will put here on the crest also another dike. Just to get a dimension of the tubes, the tailings are transported, and here they are just putting up the line to expand the operation. But let's go to the sea, and this is a specific case. You see here everything what is in here are the tailings. So this line, I hope you can see my cursor, is the original shoreline, and all these are the tailings, and the wave action distributed here in a surface of 12 square meter. And you see also there are some greenish colors. This is the remediated part at the time when we started the study. And here you have gravel terraces. What we have a transition from a marine sedimentary system into a terrestrial system with evaporation horizons. So we have in these gravels also partly horizons of anhydrite and halite. And what you see here, this left part of the river here is coming in the Locumba River. The left part is green because the local communities, they make since the 40s agriculture there. And they use the water, they take it, the natural water from the Locumba River, they take it further upstream and distribute it here. On the southern part, they did not do this. Now, after this study, they wanted to expand also the southern part. But the result is in this more than 60 years of agriculture, the groundwater level in these terraces is very high, is artificially elevated in respect to the natural level, what is here in the unused agricultural part. So the result of this is that this water here infiltrates into the tailings. And this water from the Lacumba River is slightly alkaline. It has a pH of 8. And the important thing here is it's naturally enriched in arsenic. It has about 500 micrograms per liter of arsenic. That's the natural background. And then it's infiltrating here into this remediated tailings system. And the question is now, what is happening there with this natural flux? And I can tell you yet, these tailings here, they are very poor in arsenic. They have some milligrams per kilogram. Let's around 8 milligrams per kilogram. So it's really not the source, the tailings. The source is the natural water inflowing into the system. So this is what is looking like when it's oxidizing these tailings. You have here the oxidation products, the effluent salts. We're in the Atacama Desert. Here behind you see the sea. This is a photograph of the delta. So the delta is slightly elevated in respect of the rest of the tailings. You see here this reddish. This is the expression of the ferrous iron bloom, which oxidizes here and forms ferrihydrite. So then the manager, when they bought this mine, and the director of environment, he was in charge to solve this problem. So they had at the time only all these effluent salts locally up to 0.5 meter on the tailings surface. So they was thinking what they can do. And then they have seen where this groundwater infiltrates into the surface of the tailings from the gravel terraces. They've seen that grass is naturally growing. So what they did was nothing more than using this process and making like small cells, flushing them with the water, and then after time plant this grass. And so with time they produced a wetland on the formerly oxidized tailings. So now here then of course they had to increase, they produce small dikes at the shoreline in order to be able to increase the water level to maintain the system as saturated as possible. And you see here, there are a lot of birds. It's now a stopover for the migration of the birds from south to north. So it's the biggest anthropogenic wetland and also the biggest wetland at the coast of Peru. It's highly productive when it has enough water. So the question was now, it's looking very nicely, but is it working? Has it an effect for remediation? What can we learn from this system? So they also organized always a welcome assemblage. So a lot of bioproduction there, a lot of biodiversity, enormous amount of birds. So this is how it looks. It's very typical, more or less. You have fine-grained tailings. They are oxidizing due to the fact that we are in the Atacama Desert or coast desert from southern Peru. So part of the Atacama. You have a capillary transport towards the surface of the solutes, and then you form the effluent salts. And here you see the production of the iron hydroxides, and you have low pH, therefore you can mobilize most of the metals towards the surface. And the interesting thing here is, as it's so freshwater saturated, you have mainly sulfates, not a lot of chlorides. You would think we are close to the sea, but due to the hydraulic gradient, the system is nearly completely freshwater saturated. There is an empiric formula which gives you an idea. If you have the water, the head 1 meter above the sea level, then the seawater, freshwater interface in the groundwater is about 40 meters below. So therefore, the main tailings are freshwater saturated. Only at the very shoreline you have the possibility of seawater ingression. So these are the minerals. You have chlorides, but mainly sulfates. You have some atacamite eocalcite, but it's mainly chalcodite obertate. It's a porphyry copper, so you have quite some copper minerals, but mainly major cations, sulfates, the typical variety you would expect in this. You have jarosite, you have schwertmonite and goethite in the oxidation zone. The origin is pyrite, chalcopyrite, chalcocite, and covellite, but these later two, they are minor. So you have mainly pyrite and chalcopyrite as source for acidity, iron, and copper. So this is a typical system for porphyry coppers, and that's what we did. Or mainly here you see Nuhu yet working. We did some flush drillings to obtain material from the underground. So we have profiles with the tailings core. We install piezometer nests. Here you see with drive point piezometers, pure gas sampling, and also Nuhu did a very detailed microbiological study additional, which is also in a paper specifically published. So here you see very nicely the oxidation zone with the iron hydroxides. Here some clay horizons not oxidized, and the more sandy horizons, they are oxidized and liberating the elements into the system. Here you see the coring for the unsaturated zone to obtain the pure water, which we then squeezed. And this is some example from the water in the piezometers in the depths. You see very nicely here when you let it oxidize a while, the iron, this is dissolved ferrous iron in the system here up to 6 meters. You have a ferrous iron bloom in the system, and at 9 meters you have nearly no iron. So this is for the field measurement a good method to see how much iron you have in the system. So what we did is we sampled literally all effluents of water in the system, and we did some profiles with the drillings and the piezometers in the system in the northern part where it was yet completely remediated, in the central part in the delta where it was not yet remediated, and in the southern part. I will show you here data from the northern part, and then we did also some tests of the remediation in time, how the system evolves and how fast. And this is the second part I will tell you. So the system is also from the geological point of view, as I mentioned, we have a transition of marine sediments into terrestrial sediments. So below here you have a sequence, what they call conchuelas. So it's very rich on mollusk, and they use it to produce lime. So they dredge it and produce lime with this. But of course, for our purpose, this sequence is the source of alkalinity, and you will see this also in the data afterwards below here. So these are now this first profile where you have here these 3 piezometer nests going through the remediated area. What you see here on with the green plants here, so it's water covered and with vegetation. And the left part is at the shoreline. It's still not remediated at the time, and you will see how the oxidation still liberates the elements. But now for sulfate, sodium, and chloride, you see that from the underground, here you have the head in the first gravel terrace, so you have a high hydraulic gradient which pushes the fresh water towards the sea in the system. And here you see how high concentration of chlorine, sodium, and sulfide come into the tailings from below. Okay. So here when we stop here, this means we touched the original shoreline with the piezometers. We could not go into these gravels below. So we went through the tailings, and then we had to stop when we touched the original shore. We also made a complete study of the isotopes in the system from the sulfides in order to see if it's from pyrite oxidation or if it's the sulfur from dissolution of anhydrite. As I mentioned, we have in the terraces, we have quite some horizons with anhydrite as evaporation phases, some horizons. But we also have, and these 2 samples here, you see, we have hydrothermal sources coming into the Locumba River. That's data from quite up in the Andes on the origin of the Locumba River, showing that we have some hydrothermal activity which liberates sulfur with a signature of sulfides. And of course, these waters are rich in arsenic. So this hydrothermal activity is the source for the arsenic in the Locumba River. Okay. So this is more or less a hydrogeological model of the system. So we have here on the right side these gravel terraces with the horizons of anhydrite, which has a very positive signature. And here we have then the inflow of this groundwater interacting with the marine shells, which are the sources for NaCl, sulfate, and the major cations, which then infiltrate here below into the tailings. On the top, originally, you had a nice oxidation zone, and you might know below an oxidation zone in such a strategy, you have a ferrous iron bloom, which is expressed here now with this bluish color. Now then you start remediation, and in remediating the oxidized zone, you reduce the system and you enhance this ferrous iron plume. And due to the hydraulic gradient, you push this ferrous iron plume towards the sea. And what's happening there when you push ferrous iron rich groundwater towards the sea, which is more oxidizing, so the groundwater has EH around 150 to millivolt, and here in contact with the shoreline, the EH is 400 millivolts, so you start yet partly to oxidize this ferro iron, and results in a coating of the sands in the coastline, and they became reddish. At first, this area was named Bahia Blanca from the locals because it was a white. This is usually the tailings with the wave action is the fine mafic minerals they've concentrated and transported away, and you have as a rest you have mainly quartz, so it's a nice quartzy beach. And then this quartz was coated by the iron hydroxides forming from this ferrous iron plume. So after the remediation, they observed that all of a sudden the beach from whitish, it turned into reddish, which is a clear expression that you push the ferrous iron plume towards a more oxidizing system. And then after this enters the arsenic with the natural groundwater from the Locumba River. So now what is happening with the arsenic? So here again, the system. We did also some, or we had some surprises in some drillings that we have very deep down to 20 meters. What we first saw this oxidation zone where we had iron hydroxide coatings, but a 20-meter oxidation zone below wetland is a kind of weird. But then we had to drill to see what is below, and at the depth of 10 meters, we had a nice iron oxide rich horizon, which then we could see that there are also iron reducing bacteria at the interface, so that we can see that there was a reductive dissolution of this iron oxide rich horizon, and this resulted then in the impregnation of the tailings with the secondary produced iron hydroxides. And here you have the system, how the major elements and the arsenic enters into the system and flows towards the sea. Here you have this dike, what I mentioned first. So when you have 1 meter here above the sea level, you have more or less the seawater, freshwater interface 40 meters below. So this means when you have only half a meter, then it's 20 meters. So soon this can change when you have a problem with water supply here for the wetland. So if the water level is changing strongly to drought, then you will see effects, and you will see it in the data afterwards. So again, let's have a look if this remediation worked from the remediation point of view. Here you see it's looking nicely. Here it's still oxidizing. And I want to show you some data. So here you see the pH and redox, and you see when it's still oxidizing, you have low pH in the oxidation zone, and below it's going up, and it's oxic conditions, and it's down, decreasing around 200 milliwatt. After remediation, it's vice versa. Then we have close to neutral pH and reducing conditions. So that's the purpose of a wetland. It's a reducing system, so you have no oxidation and less element mobility than in an oxic system. So let's see what's happening with the elements. If we look, for example, for copper, zinc, and nickel, the divalent cations, you see in the still oxidizing conditions, it's liberating these elements due to sulfide oxidation and lower pHs, so it's mobile, these elements. And here where you have reducing and reducing and neutral pH conditions, you see these elements are not anymore in solution. Only zinc, you know, zinc is the most mobile bivalent cation, can move slightly around if it's still below pH. But copper and zinc, it's fixed, it's sorbed or reduced as secondary sulfides. And if you look at iron, iron is mainly the source here in the oxidation zone due to pyrite oxidation or chalcopyrite oxidation. And here below you see this ferrous iron bloom. Yeah, this is typical for below the oxidation zone. And where you have it remediated, you have very low concentration of iron. Now here, this is the weird thing. Here below we have an increase of iron, and it's mainly iron 2. We did some speciation studies, so it's mainly iron 2. And as I said, due to this data, we had to understand what's going on, and we could convince the mine we need the drills. And we discovered that effectively in these steps where we discovered this increased concentration of iron and also manganese, not only iron. Therefore, it's due to reductive dissolution of this natural horizon of iron hydroxide-rich minerals. Here you see some of these horizons. This is now higher, but 10 meters below we have something similar. You have to imagine iron hydroxide-rich areas, which then under the reductive conditions of the wetland will be suffer reductive dissolution and liberate the iron into the tailings pool water. And then pushed towards the sea, it's changed to more oxy conditions and you can start oxidation and hydrolysis. And therefore we have these coatings on the quartz grains. And now the interesting part for you is the arsenic. As I mentioned, the arsenic is coming in with very high concentrations, 0.5 up to 1 point something milligrams. So 500 or 400, 2000, 200, 400 micrograms. So it's heavily naturally charged with arsenic. And then you see here, when it's oxidizing, you liberate also a little bit arsenic, but this we will see is not from the tailings. It's mainly from the fixed arsenic in the oxidation zone. And here you see where we have this iron hydroxides coating in this drill, we have very low concentration of arsenic in solution. So here the hypothesis is that this iron hydroxides coating acts as a filter for the arsenic. The natural arsenic coming in encounters here these iron hydroxides coatings on the surface of the quartz, and then it's adsorbed. And this we could show with sequential extraction. Effectively, where we have the iron input, we have also more arsenic associated to the iron hydroxide leach. So effectively, we have in this area, mainly the arsenic, at least half is still in the sulfides, or the rest is adsorbed on the iron hydroxides. And here in the upper part of the oxidation zone, you see also nicely that the arsenic at low pH conditions, as you know, is strongly adsorbed to the iron hydroxides. Okay, so the theory you can confirm here pretty nicely. So what was the effect of the remediation in Bahia de Ite? So we have this natural irrigation water, which is high in arsenic, slightly alkaline, used for the agriculture, and then with this high hydraulic gradient pushes into the tailings system. We have here below, we have the iron hydroxide rich horizon. And now we start the remediation. We change the system to more reducing and pushing this solution towards the sea. and here the arsenic is coming below. What's happening here, we're forming also by pushing or reducing the ferric ion into ferrous ion. We can push it towards the sea where it becomes reoxidized and forms these iron hydroxide coatings. And then the arsenic is fixed here or is fixed here from the iron source below due to reductive dissolution. So at the end, this, without knowing, without purpose, this remediation process produced an iron filter. As I mentioned, the tailings itself, they are not the source of the iron. It's mainly due to the iron arsenic input with the Lucumba water. So here we have the adsorption on the iron hydroxides from this from the arsenic. Now we wanted to see how fast this system evolves. Therefore, we did 2 cell tests. Here you see the piezometers below. So we have a complete profile to see how the system below is reacting. Here, this is the very moment when the water is coming in. Here you see all the effluent source. They will be first dissolved. And then with time, you see here the water changes pretty blue, a lot of copper. Here, this is new. At the start of his study, he was still laughing. Then there was a time of suffering. Now he's laughing again, I hope. And you see here after some time, when we yet planted the vegetation, you see the blackish color starting reductive sulfide reduction. Yeah, this is the first start. And then after 3 months, you see yet how the vegetation is growing. This is the cell at the coastline, very close to the shoreline. So it was easy to saturate this system. And we did then another, okay. Afterwards, we did another, in parallel, another cell in the delta, which was higher. So there we had more problems to saturate, and I will show you the result or the effect of if you cannot saturate such a remediation system. So this is first where it worked well. We could saturate it in nicely. And then you see the evolution, for example, pH. Here at the beginning, this is 550 days, a little bit, 1.5 years more or less. So at the beginning, it was acid on the top, the oxidation of sulfides produced the acid environment. Below it was neutral. So with time, first you push, when you deposit the fresh alkaline water above, you push the plume, the acid plume downwards, and then you start to neutralize. And this takes more or less 3 months, and then you have a neutral system. The redox at the beginning is oxidizing, and also after 3 months, then it's more neutral, reducing. And the effect on the dissolved elements, you see here first the iron total and iron 2, also here still high, and then very soon you decrease the concentration of this element in solution. Copper, the same, at the beginning very high, and then very soon you have copper below the detection limit. Same for silver, same for aluminum, same for manganese. So when you manage to saturate the system and you change it from oxic acidic to neutral reducing, then you can stop oxidation and you prevent the mobility of the elements in the system. So it works very well as long as you have enough water to saturate the system. But you see here, after 100 days in the surface area, we observe the liberation of arsenic a certain time. And when you correlate this with other parameters, here you see chlorine, sulfate, and sodium. So you see here simply this was a period of drought. So the groundwater level, the head of the wetland decreased. So there could be a seawater ingression into the system. And that's what you're seeing here with the greenish and reddish colors. So this is not sulfate due to oxidation, this is sulfate from the seawater. And this, of course, produced then in the oxidation zone where you have the arsenic adsorbed, because when you make the remediation in the upper part, you form these iron hydroxides, and here you adsorb the arsenic. And this is then due to anion exchange reactions liberated again into solution. And then you saturate again the system, and then the arsenic is retained again. So you see, it's quite sensitive, this system. And here, this is the remediation cell in the delta. You see it's a little bit higher elevated. We did not manage to saturate it completely. It looks nice on the surface, it's water saturated, but below we did not manage to saturate it. So the groundwater level here was about around 3 meters. So there you can see nicely that even on the top, it's covered with water, it's a reducing environment, but in between, you still have oxidation going on, you still have acidification and low pHs, and therefore you have also the liberation of the cations of iron. You see here copper, silver, aluminium, manganese. So even if it looks nicely on the top, if you do not manage to saturate the system, then you will still oxidize below. And here the arsenic also, you could not manage to really stop the mobility of the arsenic. Okay. Okay, so the conclusions about this, the construction of the wetland on the oxidizing tailings induced a change from acidic oxidizing condition to neutral reducing condition, and this only in 3 months. So this resulted in a strong degrees of metal liberation and mobility. Arsenic in the system originates from the hydrothermal natural sources in the Locumba River, while the tailings in Bahia are very low in arsenic. So this is one exceptional case that we really can confirm the source of arsenic is not from the tailings. They are really extremely low in arsenic. The remediation approach induced fixation of arsenic to iron hydroxides when you initiate on the top the wetland, and then locally reductive dissolution of underlying iron-rich layers below the tailings, which in more oxidizing condition results then in iron hydroxide coatings of the tailings material. They act then as a filter for the arsenic. And marine ingression afterwards, when you have a problem with the saturation of or maintenance of the level they had in the wetland, then you can have marine ingressions, and you have anion exchange reaction, which then in this case could liberate again arsenic. But in this case, as I mentioned, arsenic, the tailings itself or the remediation system is just a stopover from the natural flow of the arsenic via Locumba into the sea. So this is just for scientific purpose a very nice case study in order to understand what are the parameters you have to consider when you make a remediation. When you don't make the remediation well, you can produce another problem. If the concentration would be higher in this sense here, then you have to take care that you don't have any seawater ingressions, etc., etc. Okay, so the acknowledgement to the management of Southern Peru at the time, Ezio Busello, Rodolfo Risetti. We had a really exceptional support from all the staff, all the support there, and also the laboratory in Lausanne for the microbiological study. Okay, thank you very much, and hope you have some questions.
Werner, thanks a lot for this talk. I can't see you or me.
Click now. I have to say, wait, stop sharing. Yeah. Now
Okay. Yes, now I can see you. Well, this is an amazing talk about a very complex system between the continental and tailings impoundments, and also the influence of the ocean, the seawater. And I want to thank the people in the today in the webinar. We have 29 participants in Zoom and 20 in Zoom in YouTube. So I want to ask the people if they want to turn on their cameras to ask the questions, so we can have a better interaction. Somebody wrote a question in the chat, Erika Garcia. She is asking, have you evaluated the microbial participation with the oxidation of arsenic?
Not specifically. The microbiology is new. I do not see if he's connected. No, are you there somewhere? If not, but we did not look specifically for arsenic at this time when the microbiological study was.
He's here.
Ah.
He's just connected, just in time.
So he missed the talk or what?
Probably it was this issue with the time.
Yeah. Okay.
Yeah. Mm.
No, but the answer is we did not specifically look for the arsenic oxidizing or reducing bacteria. It was a more overview of the whole population acting in the system.
Mm-hmm. Another question, what about the molybdenum in the estuary during the remediation? Moly, yeah.
Well, the moly concentration here, they are also very slow in this. So most of the data was below detection limit, so we did not focus a lot of moly. And in the river, there was nearly no moly. So it was this was arsenic and moly poor system. From the tailings point of view, no? So this was at the time our focus.
Mauricio, do you want to ask the question yourself?
Okay. Yes, thank you. Yes, it's very good presentation. I am wondering if can we replicate the remediation system in different areas, like for example in the mountains.
Well, that's a very important question, and I can tell you no, because the problem is simple. Here you are on the sea level, so you can easily saturate it, okay? But if you have a tailings impoundment closing a valley in the high Andes, there the main problem is the stability of the dike. Yeah, that the dike does not fail. If you want to saturate the tailings impoundment, then you destabilize automatically the dike. And if you have earthquakes, as you have always in the Andes, this is a very specific situation you can do this. It's just to show, and it was working at this place. We had also the alkaline water to neutralize nicely. But in most systems, you will not be able to do it. Only perhaps if you have the tailings in a lake environment. Yeah, so that the technical stability is not an issue. But as long as you think a normal tailings impoundment with a constructed dike, you have to maintain, and normally the dikes are constructed that you have to maintain them dry. Yeah. Or you have a class like a fully constructed dam, like a water reservoir dam. Yeah, but usually you don't have this. You have this segregated dams where you have to maintain the dike dry. If not, it will fail. So you cannot saturate the system. Therefore, this approach works in some very specific conditions and shows when you're managing to saturate it completely. Additionally, you have a nice carbon source to maintain the system reducing. Then you can revert from oxidation to a reducing environment where the sulfides are stable, the elements are not liberated, are not mobile. But in general, it's in the end is you shouldn't do it without very thorough studies before.
Okay, thank you.
Yeah.
Bernard, I have a question. The arsenic input from this geothermal source was superficial or subsuperficial coming into the tailings? Maybe I missed that.
This is superficial. This
Okay.
is it's the drainage from the water they used for irrigation. They used the water with the 500 milligrams per liter for irrigation. Yeah. So the lettuce there you should clean quite nicely before eating it. And the Locumba River is an underground flow. So any water flows into the system underground. Therefore, it's still as arsenic-3, therefore it's nicely mobile in the system. Only when you have then the formation of this iron hydroxide coating and increasing oxy conditions towards the sea, then you can have, or if you have on the surface during the remediation, then you can have also arsenic 5. Therefore, you have it adsorbed to the iron hydroxides. Yeah, but the flow in the tailings mainly is as arsenic 3. Yeah.
Okay. Mm-hmm.
So usually it would be flow directly to the sea. Yeah.
Yes. Mm-hmm.
So this is.
So what are the concentrations of arsenic in the underground river and in the irrigation water that's coming into the tailings?
It's about 500 to 1,000 micrograms per liter.
Is the irrigation subject to evaporation so it concentrates the arsenic a little bit?
No, well, also the upstream Locumba water has this concentration. So it's originally it has around 500 micrograms per liter. Yeah. And they use this water also for drinking water purpose in a town, which is Ilo, but there they have a treatment plant.
Mm.
Okay. But for the irrigation, they use it directly without treatment plant. At least at the time when we started it. Yeah.
What are they growing there?
Everything. So you should wash everything very nicely. Yeah, we didn't bought that our veg. Yeah, that's how it is.
And the source of water is mainly this this river.
Yeah, it's the only source because you're in the desert.
Mm-hmm.
Yeah, it's nearly never raining, only every 7 years a little bit. It's still the Atacama Desert, so it's you can have a little bit of foggy area time in the year, but the water is coming from the Andes, high Andes, via this river downstream, and with hydrothermal sources in between, which brings in mainly the arsenic.
Mm-hmm. And what's the status nowadays of that site? Do you still?
Well, after we finished our study, I heard that the wetland was burning. So there it was the problem that they wanted to extend also to the southern part to make more agriculture. So they needed more water, and then you have more evaporation, less water for for the wetland, and also sometimes, depending who was in charge at the ministry, they prohibited, because there was always this fight between the mining company and the campesinos for the water. Yeah, and then sometimes, even due to the time, as it was shortly after we finished, there was they said they cannot use the water for the wetland. They had to send it directly to the sea. Yeah, so there. And after some years, I've heard that it was in the news that it was burning. So this means we had a drought again. They didn't manage to maintain the system saturated, and then the grass was burned. Yeah, I don't know by purpose, but if the wetland is burning, means that it has not enough water. No, so there was obviously a management problem. Yeah, so. And we've seen, as soon as you lower the level and it's getting drier, then it starts to oxidize immediately. Yeah, so if you don't manage the water level and you maintain it saturated, it will reoxidize immediately. So this is really a management problem. It works when you can manage it well, if you have enough water, the right water. But if, for example, state agency don't understand how it works and say, no, you have to send it direct to the sea, then you have a major problem. Yeah.
Another example of the interactions between social political decisions and hydrogeochemistry.
Exactly. So sometimes it was quite frustrating, but yeah, it's how it is. Yeah, so.
I had a quick question about reducing conditions. You clearly showed how manganese and iron was being reduced, but it never went to sulfate reduction, I take it.
Sulfate reduction only in the wetland at the surface. When this blackish dots around the plants, when they start to grow, you see nicely the sulfate reduction. But there below, no. There's no. It's
not enough carbon, I guess.
Yeah. Cecilia, mucho gusto. ¿Qué tal?
Bien. ¿Cómo estás tú?
Bien, gracias.
Lidia. Saluda a todos.
Hi, Bernard.
Hi, Cecilia. Do you have a question for Bernard?
I didn't get on time to Bernard talk, so I'm afraid that perhaps my questions are not pertinent. Sorry.
Hi, Nu. How are you doing? He did all the work. So.
I'm fine. Hi, Bernard. Hi, everybody. I'm sorry I joined late because I had another meeting just before, but I'm happy to see you again and to attend to this very important webinar. And I see here also some names I know very well. Even I did not have the opportunity to see people. Mr. Nordstrom, I think I read a lot of your publication. I'm very happy to see you again. I'm Nuhu Jabi from Senegal. Bernard was my supervisor in my thesis.
You could join us for a little while.
Yeah, and we work together in this very nice projects. And now in Senegal, we have some gold mine. In this area, we have high concentration of natural arsenic. And we are wondering how to deal with this. That we have very new mine, 10-year-old, not yet for the moment dealing with acid mine drainage, but we are trying to follow up with the mines. And we are wondering how to solve this problem because it is not natural, very high concentration of arsenic. So what would be your advice? Thank you.
You have also the arsenic, like here in this case, in the river water, or it's groundwater, or?
It is in the groundwater.
Okay, So more like in a system in Bangladesh or in the aquifer of Argentina.
Yes, yes.
Okay. Do you have any idea where is the source of this arsenic? Is it also a fan of the mountains which accumulated iron hydroxides and then also again a reductive dissolution and liberating the arsenic? Or
Unfortunately, until now, we do not have very a lot of information because there is no study about this arsenic. It is one of our objectives to see how to see from where comes this arsenic, to know maybe if you understand more the sources and so on, maybe we can find a good solution.
Mm. But you have to use this water with the arsenic for human purpose. The people are drinking this, or you need it for the industrial processes, or?
Well, these mines are in very remote area, but we have some villages using very old system wells to get water. And when I visit this area, the pH of the water was around 5 to 6, so acidic, and the level of water, groundwater, 15 meters. And some people are using this water, unfortunately. But mainly in the mine, they use in the process. It is in a very remote area. There is not a lot of people who are working there. But the problem is, from this area, after the rainy season, the water is flowing using the watershed and will get into the rivers. And the two main rivers, the Senegal River and Gambia River. Maybe
Okay.
it will be the main.
But when you say that the groundwater has a pH 5 or 6, then you have active acidification at the moment, possibly somewhere acid mine drainage flowing in.
Maybe we try several wells, and
Okay.
we see this acidic water and also concentration of metals.
Okay. And how high is the arsenic?
Well, we do not for these wells we do not measure arsenic for these wells.
Okay. Yeah, there you have to try to find out if the arsenic is coming from this acidification, so means acid mine drainage, or is it a natural background in the aquifer? So this question you have to solve.
Okay. We will continue the investigation on this topic and be in touch with you.
Yeah, of course.
And now we invite you to the following webinar because we will continue talking about arsenic, and so it could also be interesting for your research. So
yes, absolutely. Thank you. We will continue to follow. We have the program. Thank you.
Thanks. I have a question from Maria Aurora Armienta. Maria, do you want to ask the question yourself? The question was for Bernard, very interesting presentation. Which sequential extraction method did you use?
Well, we usually use, I developed one for porphyry copper systems. It's published in 2003, yeah. And it's a 7-step sequential extraction in order to track the different secondary and primary minerals which are typical in the porphyry copper system. So it's designed for this mineralogy. Yeah. So when you're interested in this sequence, you can send me an email and I send you the paper.
And this sequential extraction method that you designed was specifically for tailings. in my
Well, it's targeting any sulfide oxide system. You can use it for ore deposit. You can use it for everything. At the end, you dissolve the minerals and try to dissolve them selectively and see which elements, trace elements, or co-parasitic elements are associated. And this is not limited to tailings. It's rock. So you can use it for any rock.
Okay. Okay, so let's see if we have questions on YouTube. Or somebody else want to ask more questions? And well, we have to apologize to the people who is recently connected. We had an issue with the time in the Zoom inscription, and maybe you got the wrong message with the time, and we already fixed it. So for the next webinar, the problem will be solved. And well, I want to say thank you to all the participants and from different parts of the world, and thanks a lot. And thanks a lot to Bernard for his talk. As always, very interesting research. And well, we can learn a lot from your work, Bernard. And here a message from Carlos Monjo. Thank you very much, Bernard. Nice and very interesting presentation. And so if we don't have more questions, I think we reached the end of the webinar, and the talk is recorded on YouTube, so people can watch it again, and it will be available in our YouTube channel. So, okay, well, thank you very much.
Thanks.
Thank you.
Okay.
Thank you.
Thank you.
Bye bye.
Nice to
Thanks,
meet you.
Bernard.
Bye.
Thanks.
Bye.
Bye.